finally, it looks like the spring is here, so good news on that front. It's good. It's important to pay attention to the good news because like, if you read the news every day, then you get frustrated. But at any event, we just had well, I don't know whether to categorize it as good news, the fact that AI is taking our jobs in a way. But on the other hand, it may accelerate science. The downside is that we will not be doing the science. The AI will be writing our papers. But Miles Cranmer described it. The beginning of this future. He's from the University of Cambridge. He's not here right now because he's speaking with someone, but he will join us for his presentation at the end of the lunch. We'll start with Elia Pizzati from the CFA, who will tell us about tracing black hole growth histories and quasar light curves in a cosmological context. And then we'll hear from our own Vadim Semenov about how do these galaxies form, and that's very relevant to our own galaxy. So it's good to understand our own roots. And then finally, before we hear from Miles, we will also hear from Dominika Król from the CFA. So we have 3 speakers from the CFA today. Where is Dominika? Over there. And then the topic would be AGN-driven metallicity enrichment in the interstellar medium of Mrk573. Thank you. And then at the end, we'll hear another perspective on foundation models from Miles. So, Elia, please go ahead.
Thank you. How's the microphone? Maybe a bit closer. Okay, thank you. Nice. Okay, so hi everyone. It's well, if we haven't met before, it's very nice to meet you. I'm Elia. I'm a new postdoc here at the ITC. I've just started a few months ago. So I'm glad to have this opportunity to, well, tell you something about my research. And if you are interested about any of this stuff, please come talk to me. So I guess, well, the general focus of my research is supermassive black holes and quasars, especially at high redshift. So this is the customary plot that shows, that try to illustrate the problem of how do we form these 10 to the 9 solar mass black holes, essentially that we measure from quasars at redshift 6 and 7 in just a few 100 million years, right? This is a very well-known problem, a very old one, and indeed, like in these last few decades, we came up with many possible solutions to this problem that can be represented schematically as pathways from the bottom left of this diagram to the top right. But I think we are now in a situation, and we've been in this situation for a while, where we have all of these theoretical models that can kind of plausibly explain how these supermassive black holes form, but no way to tell which one is correct, which one of these pathways are actually followed by the real universe. Because the only thing we have is those bunch of like essentially dots in the top right corner, which are these black hole masses that we measure for the quasars. So I guess what I'm trying to say here is that I think progress in this domain will come from the empirical side of things. And for me, will come by going beyond these dots in the top right corner of this diagram. And so going beyond simply measuring black hole masses of some redshift and start talking about the full radiative history of quasars across cosmic time, which is, of course, connected with the accretion history of supermassive black holes. And I think we can actually now, at this redshift, we can actually start talking about these things in 2 main ways. One is by measuring the clustering of these quasars, and the other one is by looking at the proximity zones in quasar spectra. Now, a very, very brief introduction. So the idea behind proximity zones is that the radiation emitted by a quasar creates a region of enhanced ionization around the quasar itself, which translates into a region of enhanced transmission in the spectrum. So we see this region, right? And of course, the longer the quasar shines for, the bigger the region. And so essentially, we can measure the region, the size of the region in the spectrum, and infer what is the time scale of quasar activity. Clustering gives us something completely different. It gives us a population average for the fraction of cosmic time quasars are active. Because what we infer with clustering is something like X% of the black holes are active as quasars at this given moment. And that means that on average, each of these black holes will be active X% of the time. And that is something that we call quasar duty cycle, right? And so why am I telling you all of this? Because these constraints are finally here. We are getting closer to getting more and better measurements for this. So now we have a large compilation of proximity zones, zone measurements for these high redshift quasars. And thanks to GWST, we can use slit spectroscopy, and we can finally measure the clustering of quasars at these high redshifts. I'm happy to give you more details about these measurements offline, but I do want to kind of jump to the results. And when we put everything that we get from these constraints together, we can create a plot that looks like this, okay? Here I'm showing the quasar lifetime, so the duration of quasar activity for these very high redshift quasars, and I'm showing constraints that come both from clustering and from proximity zones. And what we end up having is that essentially these completely independent observables, right, because they're completely independent, points towards a short quasar lifetime and low values of the quasar duty cycle in a consistent way. And that is very surprising, right? Because at this very high redshift, we expect the quasars to grow very fast and kind of continuously, because they need to reach these very large masses in a very short amount of time. So we expect them to grow continuously, say, at the Eddington rate. But a continuous supermassive black hole accretion translates into a continuous radiation from the quasar. And instead, what we measure is lifetimes that are more of the order of 1 to 10 mega years. And that is a small fraction of the Salpeter timescale, which is the standard timescale for supermassive black hole growth. So this is surprising, right? And it's also exciting, I think, because these are the first real empirical constraints that we have for quasar activity at this very high redshift, right? So finally, we can go beyond saying there is just a supermassive black hole with this mass at this redshift and start talking about actually how quasars evolve across these very early times. And so I guess the question that kind of stems from a plot like this is, okay, so we have these constraints, so what do we actually learn for quasar evolution and supermassive black hole growth from these constraints, right? And so I asked myself this question after making this plot, and the more I thought about this, the more I kind of realized that these plots kind of sucks. It's like it's a very misleading way to talk about these constraints, and I think the real problem is that is the concept of quasar, that it is kind of an obstacle to really learning something here. Because if you think about this, quasar activity is an extremely complex stochastic process, right? That expands many orders of magnitude in time and in luminosity. And what we're doing when we're talking about quasar lifetime is doing an extreme simplification. We're just saying the quasar is active for some time above some arbitrary threshold, and then it turns off, right? And then we're also ignoring the fact that clustering and proximity zones probe different aspects of this stochastic process, and instead we're just putting everything together in one plot and ignoring the issue. And so that is why I think we can do much better than this. And we can exploit these constraints in a smarter way. And so I've been thinking essentially about trying to develop a new framework, a new language to talk about these constraints, and all the constraints we get from quasars, really, in a way that goes beyond the concept of quasar lifetime. And so I ended up trying to develop a full evolutionary model for the growth of black holes that kind of revolves around the concept of treating quasar activity as a complex stochastic process. Now I'll give you a little bit of details about the model. So we start from a very large n-body simulation. We need a very large one because we want to probe the rarest and brightest quasars in the universe, right? And then we extract sub-halo merger trees from this simulation. And as many other models for supermassive black hole growth do, we just paint black hole growth on these merger trees. So we make the physical assumption that the accretion of a black hole is tied to the cold gas accretion on its host halo. So each of the black hole accrete according to the accretion taking place in its host halo. But then on top of this, we add the stochasticity in the accretion process that we control parametrically, and we essentially create this stochastic process. We have some parameters that create this stochastic process, which is the quasar radiative history. And once we have that, of course, we can assume a radiative efficiency and always translate this quasar radiative history into an accretion history by means of this relation, right? And so whenever we talk about quasars, we can talk about black holes and vice versa. Okay, so this is the model in a very general sense. I need to skip through the details, but the idea is that at the end, we will have some parameters, and then we run the model, and we can hopefully compare to data So we need to build emulators to do this data comparison. I'm also not going to talk about this step here, but I'm happy to chat offline if you're interested. And then we are trying to match the data. In particular, we are considering the luminosity function and the clustering of quasars right now. And we do inference, right? And hopefully we learn something about our model and about whether our model is a good representation and how supermassive black holes grow in the universe. So this is how the model essentially performs in terms of luminosity function. And you see that we are kind of matching the overall evolution of quasar activity across cosmic time, the rise at high redshift, the peak at cosmic noon, and then the sharp decline. And that is not trivial, right? Because our black holes, the black holes in our model, don't know anything about cosmic time. They only know about the accretion on its source black hole. So it's non-trivial that we get this result. We also looked at clustering, and we are matching the clustering. I'm happy to talk about this ratio 4 offline if you're interested, but I think we do a good job at matching the clustering as well. And so in the last minute, I just want to ask the question then, what do we learn from all of this? Why, right, we now have a model that kind of represents the reality of quasar activity across the universe in a reasonable way. What can we ask then? Well, I think we can learn a bunch of things. I'll just mention a couple. One is that we can go to the local universe and look at the constraints on the black hole mass function that we have from the local universe, for example. And the interesting thing is that our model is really sensitive to these very massive black holes, which are those creating the gravitational wave background measured by PTA. So it will be interesting to figure out what kind of constraints we can get there. We can also talk about the black hole mass, halo mass relation. How is this relation shaped by our model choices, and in particular by the stochasticity of accretion versus mergers, right? This is a very open question in the field. And the last thing I want to mention is that, I mean, the thing I really care about is that we can go back, zoom in the high redshift universe, and try to learn something about black hole growth in this high redshift universe regime. And in particular, we can do so now. Yeah, this is my last slide. So we can do so now in a more meaningful way, because we can set an observational threshold, we can choose a redshift, and we can start talking about the duty cycle now in a much more sensible way, because now we really have a stochastic process, and we can talk about duty cycle in a way that makes sense. And we can also fold the light curve, the radiative history from the quasars into a radiative transfer code to essentially predict quasar spectra and see whether we match the constraints from proximity zones. So this is kind of to be done. I'll just leave my summary slide here. And I mentioned that, well, I'm happy to talk about any of the details that I skipped if you're interested. So, well, thank you very much.
So, Elia, one of the fundamental questions whether quasars are fed by mergers.
Yeah.
Right? And in that case, you will have two black holes potentially coming together. And in the process of them coming together, one or both of them would shine, and that would complicate matters a bit.
Yeah, absolutely, yeah.
And, well, I guess one way to constrain it is from LISA in the future, in a decade, but how do you deal with that in your simulation?
So right now, we are making the very simple assumption that black holes merge when subhalos merge, so it's the simplest thing we can do. We can try to add time delays, or we can try to tie accretion to mergers. We're not doing that right now. I guess the question is, do the data require this? And right now, it doesn't appear so, but we can always play around with that and figure out whether we can add more flexibility.
And then,
so yeah, the bottom panel left, that's telling you that the quasar lifetime is a few million years.
Yeah.
And as you said, that's crazy, really short. You can't make 10 to the 9 solar mass black holes at redshift 6, starting from any reasonable seed mass. So is your model actually solving that problem somehow? Can you make those big black holes?
Yeah.
Without super Eddington?
That's what, well, no, with super Eddington.
Okay,
exactly.
with it you can do it, okay.
Yeah, so our model is kind of like suggesting that if we naturally tie halo growth to black hole growth, the accretion on black holes is so rapid at high redshifts that it's kind of natural to go super Eddington. And then you see that this rapid accretion takes place. One thing I want to mention is that this super Eddington burst needs to be long enough, right? And so that's kind of something that is baked in the stochastic process that we are generating. The accretion, the super Eddington burst needs to be long enough so that these black holes actually grow.
But still no longer than a few million years.
No longer than a few million years, no. Yeah.
Okay.
Yeah, that's the
Which means
constraint.
probably probably you need tens of Eddington.
That's hopefully something that we will start to play around with with the parameters. Yeah.
To follow on what Ramesh asked, it doesn't look like it's 10 times Eddington.
No, not in this figure, yeah. So how do you do it?
It's less than 10 times, right? 1 would be 10 times.
Yeah. So we are
getting to 1.
So yeah, there is a. This is the Eddington rate. This is the Eddington ratio, but we are the accretion efficiency. That we have a radiative efficiency that depends on the Eddington ratio, and so exactly the real one will be a bit higher. Yeah, this is the luminosity. We can talk about that.
Can be much.
Yeah, it's not insanely high. It's just a bit higher, but like I think the effect is big enough. Yeah. Thank you.
Go ahead.
What redshift are you starting at, and what seed masses?
Yeah, so the redshift we're starting at is the first redshift where halos are identified in the simulation, which is around 12, because we don't have, like the simulation is huge and the resolution is relatively low. And the seed masses, we can, well, that's a free parameter, and but we essentially have seed masses that range from around 10 to the 6, 10 to the 5 to 10 to the 6. So that means that like they're not really physical seed masses. They're more like a phenomenological way. You can think about that as a phenomenological way to populate this region of the black hole halo mass relation, right?
You're not starting at awfully low mass black hole seeds.
No.
Okay.
No, we cannot do that.
It's not possible to do that numerically.
Yeah, exactly.
You will have too many. Okay, let's thank Elia again.
Thank you. I don't know how to turn it off, but you can if you don't like it.
Yeah, hello everyone. Last year, after I gave a talk here at lunch, Avi asked why some halos form galactic disks and some don't. So I evaded this question, and then I went back to my office, thought a bit more, and now I'm back to give a more substantial answer, which you can also find in this paper that appeared on arXiv a few weeks ago. Okay, so the problem that we have is we know that if we look at nearby galaxies when they're sufficiently massive, typical star-forming galaxies, where most of the star formation happens, like Milky Way, Andromeda, these galaxies are typically disks. But if we go to lower masses, so at higher redshifts, we start dealing with more irregular morphologies, right? And the question is how, like, what physics drives this transition? Why some galaxies are non-disks and some disks? So the classical answer to this question goes back now almost 50 years ago, where disks result as a result of dissipative collapse of gas with conservation of angular momentum. What it means in practice is that if we consider a gas inflowing in the potential of, say, dark matter halo, this potential can be described by this so-called circular velocity, which is essentially the amount of rotation that you need to compensate for where the centrifugal force can compensate for gravitational attraction of the potential. And then if there is some non-zero angular momentum in this gas distribution, then starting from some large distribution of, from some widespread distribution of material, which will end up in a galaxy, the gas will contract and spin up before its rotational velocity will match the circular velocity, right? So this is the classical picture. And one of the general predictions of it is that disk sizes must be tied to sizes of halos through this so-called spin parameter, or amount of angular momentum that was generated during the structure formation when the halos forms themselves from the tidal interaction. So this spin parameter is one of the generic well-established predictions of the structure formation theory, and it's of order of a few percent. And on average, this works well in a sense that disk sizes are indeed of the order of a few percent of the virial radius. But there are also multiple problems with this picture. So for example, if we go to simulations and try to find these correlations between the disk sizes and spin parameters, simulations either do not show such correlations or reveal their weak correlations, right? So there's something more complicated going on. And there were multiple papers on this, and also Ron Gron here doing very nice work together with Oliver Sear and Lars and myself. So if you want to know more about this failure mode, you can ask her. But even more generally, the mere fact that some of the galaxies do not form disks, it also tells us that there are some fundamental problems with this picture, right? Because both halos in both regimes have similar spin parameters, so why some galaxies wouldn't be disks in this case? So in the next few minutes, the global question that I'll try to address is, given some basic properties that we can predict from structure formation, such as halo masses, spin parameters, and some basic properties of dark matter distribution, whether we can predict which halos would have disks and which would not. So there are two critical missing pieces in this classical description. One of them is the fact that apart from rotation, there's also turbulence in galaxies. And so turbulence can also support gas. So in early galaxies or at low masses or high redshifts, the velocity dispersions can be quite high, so often driven by accretion and mergers and stellar feedback coming from these early low mass objects, such that the support of the material has nothing to do with the rotation. So it's purely driven by turbulent motions. And as a result, the galaxy sizes will all be also larger. So in fact, we can introduce these two scales in which the different types of support are important, and whether one or the other is bigger will be completely determined by the shape of the potential. Right? So, and this is the other missing part in this model. So if we look at typical, at dark matter-dominated galaxies, for any reasonable distribution of dark matter, we will be in this regime. So halos like NFW halos, they exhibit shallow potential. So essentially, the scale on which the turbulent velocities with these velocity scales will be supported on a significantly larger scale than the rotation. So one way to trigger this transition then is to make potential steeper, right? And this is what naturally happens when galaxy forms, right? So when baryons are accumulated in the center, you accumulate more mass in the inner region, so the rotation curve develops the peak. And for peaked distribution, the ratio of scales switch, right? Because the circularization radius doesn't depend on the shape as much because this inverse dependence. So, and this means that this triggering of this formation is very tightly related to the steepening of the potential. This is something that also was pointed out by Phil Hopkins a few years ago, and Phil will be here in 2 weeks giving a colloquium. So now from this very simple sketch, we can actually introduce a physical criterion when disks will form. So we can just equate these two scales and essentially find the galaxy radius at which this condition is satisfied. So essentially, we need to solve this simple equation, which will connect galaxies' masses, sizes, and properties of dark matter halo. And then we can also say, remember that the galaxy sizes themselves are set either by turbulent support or by rotational support. So by combining these insights, we can solve this equation. I'll spare you the details of the solution, but we need to assume something. So we can assume typical mass distributions for dark matter halos, like say W profile, which is also one of the most general predictions from structure formation models, where the profile is described by this concentration parameter, essentially how much dark matter mass is concentrated in the center. And then by solving this equation, we can get this very simple relation between concentration of dark matter halo and the amount of mass in the galaxy themselves that allows us to distinguish which potentials will be steep enough to form and support disks, and which potentials are too shallow and the galaxies will be dispersion dominated. So from here, we can see that there's a clear mass dependence, right? Because at fixed halo concentration, the galaxy must be massive enough to produce this steepening in the potential and form a disk. But also another interesting thing is that this mass threshold for disk formation, it depends on the concentration. For more concentrated halo, you need less mass in the galaxy to trigger a transition, which is very simple because if you already have a lot of dark matter in the center, you just need to add a little bit more baryons before it forms disks. So essentially, to make predictions, we need to know both concentrations and galaxy masses. So concentrations, as I said, come from general structure formation theory, while the galaxy mass fraction is more complicated because it depends on all the uncertain pieces like baryonic physics, so gas cooling, star formation feedback. So for predictive theory, we need to predict this. Or what we can do, we can validate this model against simulations, right? So for example, I can compare it to the results of TNG50, which is one of the highest resolution, most expensive cosmological simulations on the market, and where we can measure halo concentrations in galaxy mass fractions and also quantify the diskiness. And again, you see this transition from no disks to disks as a function of mass. So this is a fixed redshift at redshift 0. And then if we go to higher and higher redshift, we can clearly see how this transition shifts to higher masses, right? And this is also can be explained by this simple model, right? So it means that this redshift dependence comes from the fact that halo concentrations become lower at higher redshifts, and as a result, you need to put more baryons in the center to trigger the transition. You can make it the statement more quantitative, so we can look at the critical mass of the dark matter halo in which disks form. And the result is that this critical halo mass increases with redshift, roughly by a factor of 10. And this is something that is seen both in observations and in hydrodynamic simulations, right? And this, so it's pretty generic result. And this model naturally allows to explain this. So I'll just leave my takeaways here. So perfect. So the main point is that formation of disks themselves is related to the steepening of the potential. So it's more tied to the concentration of dark matter halo than the spin, which is very different from the classical models.
So Vadim, in your last plot, you gave the illusion that the higher the mass is, the more disk, the more likely a disk formation is. And that is if we look at clusters of galaxies, obviously they don't have a super disk there. So what's going on?
Yeah, that's good. So here I was specifically talking about the gas disk. And the idea is that if these galaxies had gas, then a lot of gas, they would form a disk, right? But they don't have gas, so.
There used to be for 20 years ago, those of us that were around, remember the days of the cooling flows in clusters. So there were claims that gas can cool in clusters. We don't see it now with Chandra, obviously, for decades. And so clusters could have had this. You would predict that if they had cooling flows, they would have giant disks, right? That would be the result of your model.
Yeah, if there were gas, it would settle on a disk, yeah. But there's no.
The reason there are no cooling flows, that's a separate feedback, presumably.
Yeah.
And so that also has to be incorporated. Feedback, whether you make a disk or not, depends on how much feedback.
Yeah, I'll need another year to think about it. But the idea is this is about a different regime. It's about onset of disk formation, which is a low mass regime. But I agree, at high mass, at high mass, if you have gas, you'll form a disk in this case. If not, you need to answer when you lose gas. And it also relates to what Andy Burkert was telling like a few weeks ago.
We see clusters, we should have seen them as giant disks, but we don't, and that's...
Yeah, because they don't have,
Yeah, exactly. Okay. Ramesh.
One piece of this story, very nice story, one piece I didn't quite follow is, are you making some assumption about the turbulent velocity?
Yeah.
It's a prescription, what, is it equal to the virial?
Yeah.
You're just saying it has to be the virial velocity
Yeah.
at that distance?
Yes.
And then it should be flat.
It should be, so this is the velocity dispersion in the galaxy.
Yeah.
And for this transition, I assume that it's viral velocity. And the idea being is that if you want to know what's the threshold for disk formation, you assume the maximal velocity that you can sustain in a given halo, which is the velocity, viral velocity, right? But I mean, for these early galaxies, you drive this velocity dispersions by accretion, right? So essentially, the idea being is that if gas falls in from the viral radius, the typical velocity dispersions that it'll impart in the ISM will be of the order of viral velocity.
Okay.
Yeah, but the assumption is, yeah, that the velocity dispersion is viral velocity.
And then you want this mass concentration in the middle so that it will require an extra rotational velocity.
Yeah, so what is how much mass concentration you need to overcome this viral turbulence by rotation? Yeah,
Okay.
exactly.
Thanks.
So, go ahead. So Vadim, if you had to summarize what you found is that we would not exist if there was no dark matter concentration in the middle of our. So we owe our existence to dark matter because the sun formed out of a disk, and the Earth is the debris around the sun. That wouldn't exist if the dark matter was not around.
I mean, I think it's. I need to think about it.
But it's
But,
interesting. Yeah,
yeah.
so the dark matter is important for us.
So how do you, maybe you can explain to me again how you get from the stage where if you're turbulence supported at the virial scale, then that's somewhat large, right? And then how do you then develop the steepening of the rotation curve if you're sort of supported at that larger scale by turbulence?
Yeah, you can think of you can think of keeping turbulence fixed and keeping angular momentum fixed, and then just ask a question. So if you keep steeping the potential, at what point this transition? At what point the scales on which both are contained coincide? Right? And this is a critical transition.
And then how does the steepening happen in a physics? Like, how do you go from the red curve to the blue curve?
Yeah, so it mainly happens because of accumulation of baryons. I can show. Yeah, I mean, actually, I think I should I show it? No, they're secret club. Yeah, somewhere. But the idea is if you just have dark matter profile, it's generally steep, shallow.
Exactly.
But it gets steeper if you increase the concentration. You need to get to pretty extreme concentrations to get steepness required for disk formation. Right? Alternatively, it's easier to form the steepness just by piling up baryons in the center, which dark matter cannot do because it's not as self-interacting as that.
Yeah. Okay.
Thank you so much,
Thank you.
Vadim. That's very interesting.
So this work will be much more observationally focused. I will be talking about metallicity mapping for Mrk573. However, it used a lot of theoretical modeling and diagnostics developed by Pei Shinzu, collaborator who is a PhD student here. So I don't think it requires a lot of convincing that AGN have a huge impact on galaxy evolution. We know that in order to reproduce observable galaxy luminosity function, we need AGN feedback. But the question about whether AGN at all and how much influences the chemical composition of the galaxy is a bit more tricky to answer. So for instance, there are different studies which are showing the radial profiles of Seyfert-2 galaxies. And you can see here 2 examples of radial profiles. On the left, NGC 7130, in which in red you can see that AGN-type regions are showing increasing metallicity with the radius. And on the right, you can see a similar galaxy, Seyfert-2 IC 5063, which is showing the decreasing profiles and very different metallicity values. And on the top of that, we know for different sources that quasars, broad-line regions, are showing general supersolar metallicities, which has been known in many years, and it's reported throughout the literature. So what we try to do in our work is we're trying to leverage the very rich data set available for Mrk573. This is a Compton-thick galaxy very nearby, and it has been observed multiple times by different instruments. For instance, you can see here the X-ray map from Chandra for the source showing soft X-rays, more or less biconical morphology, which is very common for Seyfert-2 galaxies in optics, which is seen here in oxygen-free. If we compare these 2 emissions, so X-rays with O3 contours, you see that this biconical morphology is followed by 2 of them. And in particular, the radio VLA observations are showing that also these kind of radio emission lobes are in the regions which we see enhanced soft X-ray emission. And here you can see the scales of up to around 1 kiloparsecs. So what we done is we gathered the data for this source. We used HST data with a very good spatial resolution, created narrowband imaging for that source in O3, S2, H-alpha, H-beta narrow lines. Then we also employed the MUSE data, which, because it's an IFU, we have a great spectral information with slightly worse spatial resolution, but it allows us to derive the map of H-alpha versus N2 map. And we used the diagnostics in order to derive the ionization and pressure maps, which you can see, for instance, here on the very top. But in order to calculate the metallicities only in AGN-dominated profiles, we had to also use the optical diagnostics diagrams. So what we done is here you can see on the right side of this plot, the VO-type diagram in which on y-axis you plot the oxygen versus H-beta. On the x-axis you plot S2 versus H-alpha, and thanks to this information you can divide the source into AGN-dominated regions, which here are on the left corner, marked in red later in this map, spatially resolved map. So we applied all of this information, which we have from observational data, and calculate pixel by pixel metallicities using Patient Zoo 2024 diagnostics. We used 2 different diagnostics, and we calculated metallicities for 2 different nitrogen scalings, which I will later refer as low and high. And our result is, first of all, here you can see the histograms of those metallicities. On the top profiles, you see first diagnostic. On the lower profiles, you can see second diagnostics. There is no significant difference between different diagnostics. However, what changes the situation is the nitrogen scaling. And it shifts the values. However, no matter what diagnostic and no matter what scaling, we always see some supersolar points, at least around 17% of supersolar regions. And when we actually leverage the spatial resolution of our data and plot the distribution of these high metal-rich sources, we can see that they are creating those structures. They are not randomly distributed, and they are concentrated in a certain regions of the bicons, which later, when we compare with different wavelengths, first of all, we can see that more or less the optical excitation is following those metal-rich regions, which is seen here in the contours. Now you can see only supersolar regions plotted in those 2 plots for different NH scalings. Secondly, our radio data are also co-spatial with those higher metallicity, supersolar metallicity points. And when we compare the morphology of the X-rays, soft X-rays, you can see that those enhancements really are visible also as a higher metallicity regions, supersolar metallicity regions. So all in all, we see first of all that parts of the bicones in this galaxy are supersolar, no matter what diagnostics we're using. And secondly, we can see that those regions are co-spatial with different emission in different wavelengths, which is associated with AGN activity. So when we ask ourselves how this metal get there, first, we don't see any star-forming activity in these bicones. So it is probably linked to AGN activity. And we know that the nucleus of the AGN can be metal-rich because of the broadline region metal supersolar abundances which are observed. Also, in general, in recent years, there has been a few papers which are showing that there can be certain star formation in the fragmented disks. So then we just decided to put some numbers on the both potential transportation mechanisms and secondly, the mass of the gas which we see. So first of all, what we can do is we can calculate the mass of metal-enriched gas. It is around 5 times to the power of 5 of solar masses. Also in the literature, we can find the reports of the outflow velocities and mass rates at those regions of the source. And if we calculate the timescales, which would be needed to displace that much matter, and timescales which would be needed to reach with these velocities those regions, they are comparable. Second of all, just for the sake of seeing that all of this is compatible with each other, we also, based on volumetric luminosity, calculated the expected mass rates of the radiation-driven wind. And if we assume covering factor of around 0.5, it is very comparable what we see. And here I just wanted to point out that earlier in the literature, it has been also observed that the broadline regions metallicity and narrowline region metallicity, so on very different spatial scales, up to like kiloparsec scales, they are correlated. And therefore, again, this kind of transport has been already implied. And when we look at the jets, we can compare the required power to move that sort of mass with the estimated power of the jets based on the radio measurements which we have. And again, these powers are very comparable, with jet power being slightly higher. And again, in the very different sources and using very different data, it has been shown before for Hydra A cluster central galaxy, based on Chandra data, that the metallicity is higher, which is seen here in the yellow on this map, in the regions which are also associated with the jets. So overall, we see also in very different objects and using very different techniques that there is certain association with the metal richness and the jets. So to sum up, we used the high-resolution data sets in different multiple wavelengths. We applied to them the AGN-tailored metallicity diagnostics, and based on this, we were able to resolve the metallicity to 10th parsec scales. And we found that the supersolar metallicities are present in the bicones. Then we compared it to the multi-wavelength data, and we found out that the supersolar regions are co-spatial with soft X-rays and with radio lobes. And in general, are co-spatial with the AGN activity linked emission. And so I guess that's a perfect timing. And thank you very much.
Thank you, Dominika. So these metals that are being carried by the outflow, they are produced presumably by stars forming close to the black hole, right? So is that consistent with the nuclear luminosities that are, well, I guess maybe we don't know that?
Not really. I mean, we are, one of my collaborators right now is working on, Hannelore Gerling is working on trying to put some theoretical estimates of if, assuming all of the parameters describing the source, if you can produce enough metals in those disks, and it looks good so far. It's a work in progress, but yes, it looks.
Yeah. Presumably also the broadline region is the outer part of the accretion disk that fuels the black hole, and so you make stars out there, and then the metals are carried. Yeah. Comments, questions? Looks like theorists do not argue with data. Thank you so much.
Thank you.
Okay. My name is Miles Cranmer. I'm an assistant professor at the University of Cambridge. So I gave the ITC colloquium, so I apologize to anybody in that talk because it's compressed version of that. So I want to kind of, I guess, pose a rhetorical question. To start with, I want to point out that physics is remarkably good at generalizing to, regimes or kind of data that we haven't kind of built the physics on. Machine learning is really, really bad at this. So machine learning models struggle even a little bit outside their training data. So why is this? Why is physics so much better at generalizing than machine learning? I think this is in general because physics reuses. In machine learning, every time you train a machine learning model, you start from scratch. I think, when a physicist writes down a model, they use mathematical operators. Even these operators themselves are often discovered because they're useful for modeling things in the world, and they can be composed to model other things, and this kind of biases the model towards things that are likely to be true. So physics generalizes because it implicitly reuses building blocks that have been proven useful in other contexts. Machine learning doesn't. Machine learning can do silly things. So this is an example I like to show. Machine learning model trained for detecting pneumonia in hospital patients from x-rays. And it worked really well. And then they looked at the saliency map. So this is like where the input is the most sensitive for the model. And it was looking at this token that basically said which ward of the hospital the patient was in. So it was basically just cheating. This happens all the time. Machine learning, like neural networks, are so expressive, they will pick up on artifacts you didn't know existed. So this is problematic. Now, luckily, there's been this shift in the past 5 years or so towards this idea of a foundation model. So chatbots are the most kind of pop culture known example of this. So these are foundation models for language and vision. The foundation model approach of machine learning is that you do something called pre-training. So you have this large, diverse, very general data set, and you pre-train a model on that. So you train the model to predict the next word, to fill in pixels of an image, to go from text to image, image to text. You then take this very general model that kind of understands how data is structured, and then you can tune it to specific tasks. So for example, I want my language model to be nice to the user and help them. and that's a specific task. Whereas if I only had data for that task, it would actually be really hard to train a model that generalized if that's all the data I had. So I kind of take advantage of other data to teach the model, which is actually the same thing we do in physics, right? Like when we define a model, it's not like we're starting from scratch. We're using so many different principles, even like implicit principles in our models, like things like symmetries, even the operators we use are kind of baking in knowledge about the world. So a foundation model is kind of like the purest form of this in some sense. You're just letting a model train on data itself, and then you're adapting it. So the collaboration that I'm a part of is called Polymathic AI. We're building foundation models for science. So we have an astronomy one that I'll talk about. And so I'm going to skip through this pretty quickly. So we wanted to see if we could test the same thing for physics. So what you see here in this plot is the error of a model as a function of data. So you increase data, the error goes down. Now the very bottom line, the blue line, this is a model that has been pre-trained on other data. So it's seen like other physics simulations, and it's kind of picked up like general physical principles. The green line is trained from scratch. So this is a model, it doesn't know anything about the world, and it just has to learn everything from scratch. Now the middle lines are interesting because these are pre-trained from cat videos, and they work better than a model trained from scratch. So if someone asks us like, well, how close does the physics need to be to the like physics you tune the model on for it to be useful? Actually, it seems like it can be pretty far away and still be useful. So it's, maybe something about cats not being able to teleport teaches them that eddies in turbulence can't teleport. Then the other thing Polymathic did, so we made these data sets for building these types of models. So one is called the well, one is called multimodal universe. This is basically just an aggregation of existing data in a machine learning ready format. So this involved some people from the CFA as well. And so 2025 is when we've kind of released these foundation models. One is called the Walrus. It is this kind of multiple physics foundation model. Basically, it predicts the next step in tons of different physical simulations. And it's state-of-the-art at doing this. And I think it's very good at generalizing to data it hasn't seen. So you have like a few data points for like some really expensive simulation that you want to generate more copies of. If you take Walrus and train Walrus on that simulation, it tends to generalize much better. So it needs less data to kind of get strong performance. We also have this model called ION that is perhaps most relevant to you. So this is our astronomical foundation model. The way this works is it's trained to predict missing data, because missing data is something that you can pose as a very, very general question. So for example, you take an image and you mask part of the image, and you say, okay, give me back those pixels. Or you take a spectra, you hide part of the spectra, and then you go from image to spectra. There's all these different directions you try to predict missing data that you're hiding from the model, essentially. You do this with essentially a large part of all the astronomical data we have, and you get this model that kind of speaks the language of astronomy really well, and it can adapt to new problems with fewer examples. So we see this universal, like a nearly universal improvement on kind of different machine learning tasks. So this is predicting galaxy properties from images, and you see that, so this is a problem that they haven't been trained to do yet, but you see in the data poor regime, so only 100 examples, and you can actually do like pretty well, whereas a model trained from scratch, this is like a toddler that you're teaching to classify galaxies. It doesn't understand anything. But the ION model, it already understands astronomy. It can do much better. And even in the high data regime, you see it, does quite well. You might also be interested in this. So this is called ION Search. It's basically a search engine for astronomical data using natural language. it uses ions embeddings to kind of do this in a semantically meaningful way. So if you search like 2 edge-on galaxies, it can pull up many examples of this. You can also search with images. So if you find like, oh, this is a cool galaxy, can you give me more like that? And then also add this text prompt, and it does this search. So that's one of the cool things you can do with this. And I'll stop there. Are there questions during this? I don't know. Yeah. Okay, yeah. Okay, I'll stop there.
Any questions? Yes, please.
So in the spirit of training on different types of data, pre-training, could you try to train it on, say, like physics textbooks or something like this? Is there more informational content in our understanding of physics compared to cat videos, or is it the same?
Well, so we didn't. So the models that we produced have no language in the pre-training stage. They're just numerical data. We made that choice because industry is obsessed with language models. So we're not going to have any impact there because there's money to make. There's no money to make from Galaxy images. So I think at the post-training stage, that's where you can build stuff like this, where you kind of like, you have a language model that some companies made, and you have our model that's trained on astronomy data, and you kind of like try to align them with each other. And that might be a way to kind of use that info. But yeah, we didn't feed it textbooks. I mean, that might be interesting in the future.
Was a question here? Yeah, go ahead.
Yeah, thank you for a great talk, Miles. You mentioned how useful it is for these models to consistently obey known physical laws. Is there a way to just explicitly assess how well these models are following like conservation or symmetries?
Yeah, so for the physics model Walrus, this one we can actually compute the different quantities that should be conserved. I mean, most of the time they're not conserved exactly. They violate them a little bit. It's kind of important to not bake in the physical laws because there's certain systems like in experimental data sets, for example, where the simulations might actually be a little bit wrong. And you actually want to tune on experiment and kind of find like the additional physics. But the model itself, like it does kind of violate conservation quantities a little bit. So there's a trade-off between, oh, this is going to give me simulations really fast, but they're slightly less accurate. So then you have to make the choice. Yeah.
Well, given the exponential improvement in AI capabilities, presumably if you give the same talk next year, it will be much more impressive. We cannot really catch up, right? And so we look forward to your next visit to see how things develop. Thank you so much, Mike.